Hi again. I hope you have out lecture notes for lecture 60, confidence intervals for the mean. And I say here in hypothesis testing, which is what we've been doing for the last who knows how long, we've been testing two different hypotheses, null and alternative, about a given population parameter. What do we look at? We'll look at the mean, difference of means, population proportion, standard deviation, difference of standard deviations, difference of population proportions. We were doing hypothesis testing with all that, and what that meant is we had a preconceived notion of what we thought the value of the parameter was, or the difference of the parameters, or what we thought it might have changed from. So we had a null hypothesis, which said it was some value, and an alternative hypothesis, which said no, it wasn't. It was bigger, or it was smaller, or it was not equal to that value. So we kind of started off with a preconceived idea of what we thought the parameter might be. Now what we want to do is we want to look at a situation which I think often has maybe more widespread application, and that is we have a population data and we don't have anything that we know ahead of time or think might be true ahead of time about the population parameter. We don't know what the mean is, for example. We don't even have an estimate or a guess of it. And what we want to do is actually estimate its value. All right, so I say here, how to estimate the population mean mu. That's what we'll start with. So that's, I think, the simplest one. And, well, you'll take a simple random sample and compute the sample mean x bar. All right. And I say, since the sample means taken from various samples tend to cluster around the population mean, we expect that x bar will be a good estimate. And I just want you to draw a little picture here. So here's the number line, and all possible numbers, and maybe here's the actual value of mu on the number line, and we don't know where that value is. We don't really know that it's there, say, but we take a sample, compute x bar, and maybe x bar is, right there. Okay, like I said, x bar tends to cluster, the values of x bar tend to cluster around the mean. If we were to take a bunch of samples and compute a bunch of x bars, we'd like to think of them clustering around the mean typically. So if I were going to just take my best guess as to what mu was, I would just say, hey, I think it's x bar. That's my best guess. So I say here, we call the sample mean x bar a point estimate of the population mean. The idea being, if I said, give me one number, one point on the number line, that is your best guess as to the population mean, well, take a sample, compute x bar, that's my best guess. So right there's my best guess to what mu is. And of course, we know that the values of x bar cluster around the mean. It's not likely that we'll hit the mean right on the head as I did here, right? So I say this, it's not likely that x bar exactly hits mu on the nose. How far off is it? Well, keep in mind, I don't really know where mu is. I just have my x bar here. So, mu's gone, and I just want to, I just have an x bar, and that's my best guess. How far off is it? Well, of course, I don't know. If I knew, I could make that adjustment and that I'd know exactly what the mean is, but I don't know that. So I can't tell exactly how far off it is, but can we tell how far off it is likely to be? If we allow a little probability, a little uncertainty in there, and the answer is yes, we can provide an interval of values about x bar within which we can have a high degree of confidence that the true value of mu lies. So if the true value of mu really is here, maybe if I didn't know that, but I got my x bar here, could I come up with some interval, that I could start at x bar and go maybe up this far and go down that far, and I could have a high degree of confidence that I actually captured the value of mu inside that interval. And we can certainly do that. Of course, the easy way to do it is just to let the interval starting at x bar go out to infinity this way and out to negative infinity that way. And of course, we're going to capture mu, but that's kind of a worthless interval. What I'd like is as small an interval as possible that sits around x bar, such that I'll still have a high level of confidence, a high level of reason to believe that mu is inside that interval. Right? That's where we're headed. Okay, so I say to do this, we need to recall some basic ideas from probability and random variable theory. To make things simple at first, we wish to know the population mean of some population of data but we somehow already know the population standard deviation. So just assume that we want to know what mu is, and we happen to know what sigma is already. We did this way back when we first started hypothesis testing. We did hypothesis testing for mu, assuming we already knew sigma, which, as I said, most of the time is unrealistic. There are applications where that can happen. Most of the time that's sort of unrealistic, but it's a kind of an easy way to start getting the ideas down, and we'll move to where we'll assume we don't know sigma soon enough. But so we're going to start off assuming that we want to estimate mu with some interval of possible values, but we happen to know the exact value of sigma. All right, so what can we say? We know that then for a large enough sample size n, the central limit theorem, CLT, says we can assume, if we pick a sample size n big enough, we can assume that x bar is normally distributed with mean mu, this unknown mean, and the standard deviation is then sigma over the square root of n, where n is the sample size. Okay, so we can make that assumption so that, you'll see I write so that in there, so that if we do a little algebra on this, what we end up with is that x bar, well, let me say what it is. It's the z-score. So that the z-score, x bar minus mu over sigma over the square root of n is normal 0, 1. All right? And this means if we can make this computation, we have a new random variable that is a value of a new random variable that comes from the normal 0, 1 distribution. And I point out here that I say for large enough n, generally for n bigger than or equal to 30, this is true for smaller n. Also, if original population is normally distributed. All right, so it's true for smaller n as well. So if you remember that just from all our working with hypothesis testing, I just want to refresh your memory. So I say here, think of our z-score graph with critical values. I'm going to throw in these critical values of z alpha over 2 and negative z alpha over 2, where alpha, from hypothesis testing, alpha was the significance level, right? So we're going to have a kind of a different way to think about it here, but it's essentially amounting to the same thing. So let me just draw the picture that we've seen many, many times. So you have our z-score, our z random variable curve here, and let's say that about right there is z alpha over 2, and so I come back symmetrically over here and I'd have negative z alpha over 2. So all of this should be quite old hat. This means that this area or this probability is alpha over 2, correct? And this tail probability over here, you see, yeah, is alpha over 2. Okay. Well, and this is, again, this is for, the random variable here that we're looking at is the z-score, so this is for x bar minus mu over sigma over the square root of n. We are saying if we have values of this random variable along the real line, if we were to do it millions and millions of times, we would fill out this kind of a probability density curve. Okay, but there's something that we have never really looked at in this class, not much, that we're going to now look at. We spend a lot of time looking at tail probabilities when we do hypothesis testing. But what we're going to do now is look at what's in between, this area in between here. The probability of this area is equal to, well, look, I have alpha over 2 out here, alpha over 2 out here. So put them together, I have alpha. This is like I'm doing a significance test, a hypothesis test that's two-tailed with significance level alpha, right? I put half of alpha here and half of alpha here. So I put it together, both tails together have alpha, which means, remember, the whole area under the whole curve has to be 100%. So this probability here, this area here that I've shaded pink, must be 1 minus alpha, correct? So that's what I have for the z-score here of x bar. So the probability that this z-score lies between negative z alpha over 2 and z alpha over 2 is this 1 minus alpha, right? I think that's what I say next. Yes, we can say that on the next page, x bar z-score, given there, lies between minus z alpha over 2 and positive z alpha over 2 with probability 1 minus alpha. What this says is that, I guess I can use this here. This says, so go right below there. This says, how do I word this? That, now watch what I'm going to do. I'm going to say that this value lies between this negative number and this positive number. It's the same number on both sides, just that it's negative over here and positive over here. So if you remember from high school algebra, if I put a bar on either side of a number, that's the number's absolute value. So this number can be positive or negative, right? If x bar is a little bigger than mu, it's a positive number because that down there is positive, so positive divided by positive is positive. If x bar is a little smaller than mu, I get a negative number on top. When I divide, I get a negative number. That's why I can go all the way down to negative z alpha over 2 and all the way up to z alpha over 2, and in there, I have a probability of 1 minus alpha of landing in there with this value. Okay, so that says that if I just think of the absolute value, which is sort of like thinking of the positive value of it, it's got to be between 0 and z alpha over 2, correct? Because it could be any positive number here, or it could be any negative number back here, and a negative number back here. If I take its absolute value, that puts it over here. So really, I'm saying the absolute value has to be less than z alpha over 2, correct? Doesn't that make sense? It's certainly bigger than 0 if it's absolute value, bigger than or equal to 0. But it has to be less than that, so I get just this half of it for that positive, for the absolute value of it, meaning I get for whether it can be positive or negative, I get the whole interval. Well, let me do a little algebra here. If you remember, man, this is something that, I have to kind of come back to you maybe. I have a fraction here. It's inside an absolute value sign, but this thing on the bottom here is a positive number anyway. So I can swing it out, multiply both sides by it if you like, and that would clear it out of this denominator and put it over here. So I have x bar minus mu, an absolute value, is less than z alpha over 2 times sigma over the square root of n. All right? Here's where we do maybe, I don't know, the most algebra that we've done. We won't have to do very much here, and then we'll be done with it. Okay, what does this mean? I guess I will say, I will say that when I take the absolute value of the difference of two numbers, what that gives me is the distance between the numbers. The absolute value of 4 minus 7 is what? 4 minus 7 is negative 3. Its absolute value is 3. I've just told you that the distance between 4 and 7 is 3, correct? That's what the absolute value of a distance gives you. Okay, so I am telling you that this number and this number can be no more than this distance apart from each other. So this says that, well, I'll write that in. X bar and mu are less than this much apart. Have one more thing to write. So it must be true for the squeaks, it must be true that mu, if I think of starting at x bar, how far away can mu be? It can be no more than that distance away below or that distance away above. So mu must lie between x bar minus this number and x bar plus this number. All right, mu must lie between x bar minus this and x bar plus this. That's saying that it's no more away from x bar than that number or that number, either down or above, below or above it. In fact, let me just say it like this. Let me not say must lie. Let me say it lies between that number below x bar and that number above x bar. And let me say, comma, this is all assuming we're looking at that interval where the probability is 1 minus alpha. So it does this with probability 1 minus alpha. All right? Okay. So come back. We're going to see this all again, especially we're going to see it all in some examples. But let me just refresh a little bit here. I am saying that if I pick compute a value of x bar, mu with probability 1 minus alpha will lie between the number x minus this thing, x bar minus this thing, and x bar plus that thing, all right? Okay, now I have a little bit more to say, and then we'll do some examples, but I want to add one more word here, and I know this is a little bit heavy. We haven't done anything like this in quite a while, I don't think. We're just about done to where we can work some examples. What we are thinking, folks, is we are thinking of taking a sample, computing x bar, and then doing these calculations. If we do that, the taking of the sample and the computations, those are then in the past, so they've already happened. We usually think of probabilities as referring to something that's going to happen in the future. Before I take the sample, the probability is 1 minus alpha that mu will lie between here and here before I take the sample. But after I've taken the sample, it's kind of a done deal, right? So we don't usually use the word probability anymore. We start using a different word. We use the word confidence. All right? It's kind of like if I flip a coin, as I'm flipping it, or before I flip it, the probability that it's heads is 1/2. But after I flip it and before I look at it, it's already determined whether it's heads or tails. It's not really correct to say the probability is still 1/2, but I don't know what it is if I haven't looked. So I don't want to say the probability is 1/2. I might say, I don't want to say the probability is 50%. I might say I'm 50% confident that it's heads. Okay, so it's a minor distinction, and the way we do the computations, we'll still just kind of think of it as probability, but technically we call it confidence. If it's after we've taken the sample, gotten the data, and done the computations, we're now looking at confidence levels rather than probability. Okay, so what do I say below here then? For a generic value of alpha, we will speak of a 1 minus alpha confidence level, or what is more standard, a 100 1 minus alpha % confidence interval. We call this value right here that we are adding and subtracting from x bar, we call that the margin of error and denote it as E. So look what we have here. The summary of everything I've talked about so far is right here. So, given alpha, given some, we can, we usually think of that as a significance level in hypothesis testing. Giving some alpha, a 101 minus alpha % confidence interval for the mean mu of a population is x bar minus e, comma, x bar plus e, where I use these angled brackets. And E, remember, is this value right here. So I'm talking about x bar minus it and x bar plus it, and I'm saying mu is between those two values. And what does this mean? This is an interval notation. And it means, I'm looking on the number line here. Here's x bar, and if I go up a distance e, I get x bar plus e. And if I go down a distance e, I get x bar minus e. And what I'm saying is that the value of mu is somewhere in between here with my confidence level is 1 minus alpha. If you can squeeze that all in there, I hope you can. Because then what I say then below is this can be written in two other ways. How else can I write this interval indicating all this? Well, I can do it with this number line, but that wasn't a way I was talking about. Another way to write it is, in the book, I think some books at least like to write it like this. X bar minus e is less than or equal to mu, which is less than or equal to x bar plus e. This says that mu is between this lower number of x bar minus e and this upper number of x bar plus e. And another way to write it, which is maybe even kind of nicer, is just x bar plus or minus e. And that's understood to mean everything in between x bar minus e and x bar plus e. Okay, and I think I have here, it's just some quick examples. Okay, so. We'll do some more complete examples in the next lecture, but I want to do some quick ones just to make sure we got the computations down and can see how to interpret them. Okay, so suppose our population, next page is, suppose our population, mu is unknown, but we happen to know that sigma is 8. So mu equals, I don't know, this is example, and sigma equals 8. Okay, we wish to estimate mu. We take a simple random sample, n equal 36, and we get that x bar is 143. Okay, so our best point estimate, if we just wanted to give one number as our answer, there's our best answer for mu. But we can do better. We can get that little interval that we just were talking about. So I say here, number one, this is how it's usually stated. Find a 90% confidence interval. For mu. Change colors here, see if that's a little bit better. Okay, well, the answer is, it's x bar plus or minus e if I use this notation, right? And I know what x bar is, it's 143, but I just have to figure out e. So e equals, what does it equal? It equals z alpha over 2 times sigma over the square root of n. Well, look, sigma is 8. And n is 36, so I can plug all this in. I just have to figure out z alpha over 2. So, of course, what I need is, I can read that easy enough from the table if I can figure out what alpha over 2 is. I need alpha over 2, right? But that's easy. 90% is a 1 minus alpha percent, 100 times 1 minus alpha percent confidence interval. So I know that 1 minus alpha is 90% or 0.9. Right, so alpha, work that out, alpha is, do the arithmetic or the algebra, alpha is 0.1. So alpha over 2 is 0.05. So I need z of 0.05. That's the critical value that has, in the z-scores, that has 5% of the area to its right, and that is 1.645 if you look it up or if you don't already have it memorized. All right, so I just plug all that in then. So E equals z alpha over 2, 1.645 times sigma 8 over the square root of 36, and that works out to be, what do I have? Yeah, 2.193 repeating, and since we have been given data, let's see, I guess my data is to the nearest integer, the statistics I computed, x bar is to the nearest integer. I should probably only compute this to the nearest integer, but I'm going to go ahead and just round it to the nearest tenth. All right, so that's to the nearest tenth. Typically, you'd round it to the nearest digit that you have your other statistics calculated in terms of, which we said is one more than what the data is. That's just kind of a standard there. I'm going to do one more here because I should have written this as 143.0. In fact, maybe if I remember before I post this, I'll make it 143.0. So it is to the nearest tenth. Anyway, that's our margin of error. So our confidence interval, x bar plus or minus e, that's 143 plus or minus 2.2. So we can say, if I subtract, I get 140.8. And if I add, I get 145.2, I do believe. There is my 90% confidence interval. CI is often how we abbreviate confidence interval. Next one, find a 95% confidence interval for mu. That's number 2 here. Folks, almost all the work is the same. Well, it is the same, except 95% means our alpha over 2 is different. You should see that alpha is now, 1 minus alpha is 0.95, so alpha is 0.05. So alpha over 2 is 0.025. And z 0.025 is 1.96. That's the only difference. I take 1.96 and put it in where 1.645 was. Everything else works out the same. So if I do that, I get E is 1.96 times 8 over the square root of 36, and that works out to be 2.613, so we'll call that 2.6. So the 95% confidence interval for mu is, I'm going to go down from 143, I'll go down this time 2.6, right? So I get 140.4, and then go up to 145.6. Okay, it's easy enough, right? Once you get this down. We're doing a lot of the same calculations we do with hypothesis testing, but it's just used in a little different way. Notice that for the same data, if I want to be more confident that I captured the mean, the true population mean in my interval, I have to have a bigger interval. That's a bigger interval than that one is, isn't it? So it's gone down a little lower and it goes up a little higher. I have to if I want to be more confident that I've captured the mean, because you know, here's X bar, and if I go up this far and this far, I have a certain confidence level that I've captured somewhere in here the true value of the mean. If I want to increase that confidence level, I got to cast a wider net, right? You got to cast a wider net to be more sure you'll catch the fish. So it should make sense that if I want to up my confidence level, the interval gets wider. So you see there's a little bit of a trade-off. I would like to have real high confidence that I've captured the mean, but in order to do that, I got to have a wider interval, which isn't so good. I wish I could just nail down exactly where that mean is, or down to just a tiny little interval with very high confidence. But there is this trade-off. We'll look at how to deal with that trade-off a little more later. But if you'll let me, I'm going to push forward here because we want to get to where we are really ready to do some good solid examples. So let's see. I say they're at the bottom then. Most of the time we want to estimate mu. When we want to estimate u, we don't know sigma, right? It's kind of a fluke if we happen to know sigma. So instead of the z-score, the central limit theorem leads us to x bar's t-score. X bar minus mu over s divided by the square root of n. If we do all that algebra before, everything is the same, but the margin of error is what I want you to write here. The margin of error is now t alpha over 2, and it's s over the square root of n. Everything else goes through as before. So let's do a couple of quick examples again. Suppose in our population, this is the last page of this lecture, both mu and sigma are unknown. We wish to estimate mu. Take a simple random sample of size n equal 64, and we compute x bar is 28 and s is 16. Find a 95% confident interval for mu. All right, that's number 3. Alpha over 2 is 0.025 again, okay? So I want to look up t, 0.025, and if I go looking it up, I get 2.00, and what I'm doing is I'm using degrees of freedom. I should use 63, but the table I have doesn't give me 63, so I use 60, right? So I go below, as we always have. All right, so E then, the margin of error is t 0.025 times s, which is 16, divided by the square root of 64. And if you work all that out, it's 2.00 times, it's 16 over 8, so you end up getting 4.00. There's your margin of error. So the 95% confidence interval for mu is, my x bar is 28. So I have over here x bar equals 28. How to have that? So 28 minus 4 is 24. Probably I would go to the nearest tenth, 0.0. And 28 plus 4 is 32. So I'm 95% confident that the true value of the population mean lies between 24 and 32. What if I want a 99% confidence interval? I want a higher confidence level, so I should expect that I'm going to have a wider confidence interval. So this is number 4. Very quickly, alpha is 0.01, right? Because 1 minus alpha is 0.99. So alpha over 2 is 0.005. So I need to find t 0.005 and take that times 16 over the square root of 64. And when I do all that, I get 2.66 there times 2, so I get 5.32. And if I round it to 5.3 to the nearest tenth, I have from my mean of 28, I go down 5.3, getting 22.7, right? Listen to me carefully. That's 28, the mean, the sample mean, minus the margin of error. And then 28 plus the margin of error is 33.3. So this is a 99% confidence interval for mu. Okay, we will look at more thorough examples, and we'll have kind of a nice way to lay everything out in the next lecture, but we will stop here.